Hi, I'd like to talk to you about something that I occasionally get questions about in my A-level physics classes, and that is time travel. Some of my students are very interested to know whether time travel is in fact possible. To be perfectly honest, I don't really know that much about the specifics of how time travel could theoretically be accomplished, but I do know something about a couple of related issues really, about the same type of subject. And this occurred to me when I was watching a film about time travel called The Time Machine. And in the film, you see someone travelling through time in their time machine. As the camera pans away, you see everything. If he's going forward in time, you see everything aging and decaying. And there he is in his time machine. It's kind of time is, I guess, staying constant for him or progressing much more slowly. I was thinking about this issue. And also the question that is often, or not really, it's a question, but it's posed in response to, can time travel be accomplished? The question in response to that is often put like this: if time travel is possible, where are all the time travelers? Surely if time travel is possible, then in the future someone will discover how to do it practically, and then they'll come back in time and they'll present themselves to us and they'll say, hey, we've travelled through time, we're from the future, we would like to tell you about that and prove to you that time travel is possible, or maybe there's in consequence of that they show that time travel is possible. That of course assumes that they want to come back to us at this particular time and prove that, and also that we'd accept that they're not crazy, they haven't lost their minds, and they're not just a crazy person claiming a hoax. Okay, so in that question, where are all the time travelers, maybe there is an answer to that time travel is possible, but maybe the time travelers didn't make it here. So let's think about that. What we're going to do is going to use some basic A-level physics to think about a related issue to time travel. So, you're constructing a time machine, you're a clever person, you've figured out how to do it, you're constructing it, assume that you're a human being doing this. If you're a human being doing this, you're likely going to be on this. You're going to be on Earth constructing your time machine. And so you've nailed it, how to travel through time. You built your time machine and you're about to do it. So as you're travelling through time, why would your time machine know to update its location? You see, the thing is, let's say you're somewhere on Earth over here. The Earth is rotating, quite quickly in fact. And as it's rotating, how does your time machine know to keep up with that rotation of the Earth, so that when you come back out of travelling through the space-time continuum and however that is done, that you don't end up in the middle of the Atlantic Ocean or the Pacific Ocean or inside a mountain or something like that? Your position is important because you're on an object that is moving, it's rotating very quickly. So position is key. You've got to be able to have some way of changing your position whilst you are out of the ordinary space-time continuum. And how would that be done? I mean, normally when we're changing our position, when we're in the space-time continuum, we do that usually by an application of Newton's third law. We push something back and that thing pushes us. Take walking, for example. I push the floor back and the floor pushes me forward. Or if you're in a car, we rotate wheels, we push the ground back and the ground pushes the car forward. Or if we're thinking of aircraft or spacecraft, we propel something out the engines backwards that propels us forward. How is that done when you're not in the space-time continuum? I mean, if you could nail that problem, I think that would be a tremendous achievement, to be able to come up with some new method of propulsion or changing your position that could work out of the space-time continuum. That is pretty crazy to think about how that would be done, actually. So you've got to be able to deal with your position. We can actually use some quite straightforward A-level physics, like I was saying, to kind of quantify what we have to be able to achieve with our time machine that actually needs to be a space-time machine, really, because of this position issue. So the radius of the Earth is 6,400 kilometers, 6.4 times 10 to the 6 meters. And the rate of rotation, or the period of rotation, is 24 hours. It takes 24 hours for the Earth to rotate. So using that data, you can ascertain that in just 1 hour, if you wanted to travel through an hour, the kind of distance that you would have to compensate for is 1,670 kilometers. So that's not an insignificant amount of distance you need to cover whilst you are out of the space-time continuum. And that's not only it. You know, the Earth is rotating, sure, but the Earth is also orbiting the Sun in the solar system. So we're going to have to account for that as well. So that's already added, you know, perhaps you could say if it's roughly circular motion. I'm using circular motion here, of course, so I didn't mention it, but and the Earth is not perfectly spherical, so you need to get a little more complex than what I've come up with here. But I didn't write on that our distance actually is 1,670 kilometers. So that's the kind of distance you have to compensate for just due to the rotation of the Earth. And if we assume circular motion for the orbit of the Earth around the Sun, and we get some data here, so the orbital radius is 1 astronomical unit, and that is 1.5 times 10 to the 11 meters. And the orbital period is 365 days, which is 3.15 times 10 to the 7 seconds. So, I mean, when you use that data to find out what kind of distance you're going to have to compensate for with your position, then you get a value of 180,000 kilometers, which is enormous. So you need to be able to compensate for that whilst you are out of the ordinary space-time continuum, the stream of time. So yeah, this is actually very, very important. You need to be able to compensate for that. So you know, let's say your time machine was on Earth, you really need to get this right, because if you come back into the stream of time and your time machine is now where they've built a building, or where some new mine has been dug beneath where your or new quarry has been dug where your time machine was, something like that, and you appear there and your time machine drops a huge distance, or you actually merge back into the inside of a new mountain or something if you're traveling really large frames of time. You know, the list goes on. There, you've got to get this right, or because of the orbit of the Earth around the Sun, you miss the Earth and then you're out in space. So you need a spacecraft time machine, really. And even if you were using a spacecraft as your time machine, which was orbiting the Earth, presumably, or something else. But anyway, you've got to keep up with the Earth, because otherwise you could end up on the other side of the Sun the other side of the Earth with the Sun in the middle. So that's a huge distance away. Is your time machine going to be able to sustain your life whilst you're over there? And would you be able to get access to the energy resources you need to jump back in time if that wasn't the case? So yeah, this needs to be got right. And there are other types of motion that we need to consider as well. The galaxy is moving through, the Sun is moving around the galaxy is moving through space in the universe due to the expansion of the universe. And all these things, they all add up to eventually a very complex set of equations that you're going to need to solve to make sure you get it right. And like, if you think of the expansion of the universe, we're only benefiting from a few decades of accurate or precise data here. So certainly at the moment, we probably wouldn't have enough information to perform the necessary calculations to travel through time. But would we have enough information in the future? Would the dark matter problem be solved, the dark energy problem be solved, in order to give us access to that information that we can then calculate? So just to kind of give a bit of an animated context to what I'm talking about here, if we look at this animation, which has been going around on social media for a while, if I can update the slide here. There we go. Okay, so I'm not saying whether this is accurate or inaccurate. I think there's some questions about the orientation of the solar system in this particular animation relative to its motion. But this is a picture of the solar system. There's the sun there, and the planets are orbiting the sun, and the sun is orbiting the centre of mass of the Milky Way. And so as it does so, obviously it's carrying along the whole solar system, and you get this wonderful corkscrew spiral effect, which is pretty mesmerising to look at. Now, whatever the orientation of the solar system, so I think that the solar system is probably in the same plane as the galactic plane. Don't quote me on that, I could be wrong. But anyway, the kind of motion that you're going to have to be able to calculate for, just for thinking of the rotation of the Earth around the sun as it orbits the galaxy, is this kind of path, this kind of corkscrewing path. You're going to have to be able to calculate for that. And that's not even taking into effect the rotation of the Earth, and it's not even taking into effect the expansion of the universe. So those are other things. So all the motion gets overlaid on top of one another, and you get this really complex resultant motion that you'd need to be able to calculate for. So when you build your time machine in the future, please make sure you account for this so that you can successfully come back into the space-time continuum at the right place so that we can celebrate your achievement, because you're clearly incredibly intelligent, and you're the kind of person that the human race could do with if you can build a time machine. We want to keep you alive, so please make sure you come to the right place. Thank you very much. So I've been talking about position and the fact that you need to get that right for time travel. In another video, I'm going to discuss a related issue to this, something else that you absolutely must get right for time travel. So look out for that video. I hope you found this interesting to think about. I certainly did, and hopefully you'll find the other thing interesting to think about also.